my God, have you read, hang on. What the hell was that book I read years ago? I think it was Fast Food Nation.
Oh,
They actually have photo shoots for the food where they put makeup on it, essentially.
Really?
Oh yeah!
They
spray.
to make it look greasy.
They treat the food like a model. And they make it look that good. You get it, you're like, what the hell is this? Somebody sat on it. And it's not a joke. There's an industry in that. The marketing of food, it's crazy. Yeah.
Wasn't there just the legislation passed that they can't do that anymore?
I hope so.
I
hope so.
Recently. They only started that like super recently.
Yeah, like
I'm not saying you don't.
You guys seen all the stuff they
Just saying they dress up food sometimes.
They pull the slice and have the cheese. They like screw the pizza down to the table and then just pull out the white piece to make the cheese do that. Yeah, to make it like gooey.
There's some interesting, that book, Fast Food Nation, was very eye-opening for me. It made me fall in love with In-N-Out, first of all. That place is ridiculously awesome. In-N-Out Burger down in California.
So good. In
So,
Nevada, too.
in Nevada, yeah, they're everywhere except Bend, where I asked them to come. I actually sent them an email. As soon as I got back from visiting the first time, I was like, please build a In-N-Out in Bend. Within 2 hours, I got a phone call from them thanking me for my email. I'm like, who does that? Like in 2000, whatever that was, 2000, who calls back? So anyway, and they said they wouldn't because we're too far from their local suppliers. I was like, you're in Utah? And they kind of like, yeah, well, and they wouldn't. I think there's one in Texas too now, which is strange. I guess local means like Arizona. I don't know. But it's a very interesting read if you want to, kind of if you want your eyes opened about the fast food industry. Just Fast Food Nation is very interesting. But anyway. I want to talk about today this idea of these things called outliers. And there are many, many, many ways to identify them mathematically. And I want to talk about a few of them today. A few of them. But what I really want to get into today isn't to get nitpicky about any one way being better than the other. What I want to talk about is a very general definition of them. Actually, I do want to get into that. I want to get into it a little bit as far as identifying, because I don't want you guys having to wrestle over this definition. Outliers are simply data points that are atypical when compared to other data points in a data set. Data set. The key word is atypical. There's a great book by Malcolm Gladwell called Outliers. He's written a few. Outliers is a fun one. He kind of looks at it very, very generally, the idea of outlier people, outlier performances. One of my favorite parts of that book was when him and his wife were at a hockey game, I forget where, and his wife noticed that a lot of the players on the team had birthdays that were in January and February. He's like, that's kind of weird. Like, why would you think that? Like, why would there be a lot of birthdays in January and February on a professional hockey team? Say that again?
Because they used to be cold weather.
I don't. Well, they were from all over the world. Then they were from Russia. They were from cold weather climates for the most part. And he looked into it, and it has to do with when a professional hockey player starts playing hockey. They start at a very young age, Pee Wee leagues, and the age cutoff for that, January 1st of any given year. So a kid that's born earlier in the year at age 5 is going to be that much bigger than a kid born in October in that same year. Therefore, getting into the sport larger than the kids around him, therefore doing better in the sport, therefore getting that jump start. And I encourage you, next time you're at any professional sporting event, check the birthdays if you can get the program. It works in soccer too. I checked it at the last Timbers game I went to. I'm like, son of a bitch, like 80% of them the first 3 months of the year. Because that's when the age cutoffs are for those Pee Wee leagues. And that's when it all starts. Very rarely do professional athletes jump in at age 18. I'm going to be a professional soccer player now. No, you started when you were 4. And you've been playing ever since. And you got that jump start. You were a little bit bigger, so you were a little bit better. And you're a little bit better, so you caught the attention of the next coach. And then better coaching, and boom. Which is why I go find the guys that were born in December, give them a high five. You're the man. Awesome. Please, John.
Intro to Soch with Ken Ruckers. He actually has the book out, I think.
Yes, Malcolm Gladwell. Yeah.
And the exact topic is totally discussed.
Oh, that's what I'm saying. I got it from Gladwell's book. That's what I was mentioning. Yeah. That's one of the many things he talks about in that book. Is that I love it. It's a fantastic read. His other ones I haven't had a chance to read yet. The Lane, Tipping Point. But the idea of that book, though, is to kind of look at this more generally. What I kind of want to do today is I want to look at it more specifically. I want to talk about how you can mathematically define outliers and kind of reason through what makes an outlier. So I mentioned in this last data set that we just had up here, the one we're going to look at again, I looked up at the box plot, I said, wow, there's an outlier up there. And you're like, wait a minute, why would there be an outlier up there if the data points are 0, 1, 2, 3, and 4? And I said, well, one of the definitions of outliers is being demonstrated right now. So what I want to do is I want to look at 2. Well, one at a time, I guess, one at a time. The first one is, well, first of all, let me ask you guys. We've been throwing around the term a lot, outliers, outliers, outliers. Sometimes I think students confuse outliers with what? Good, extreme values. I like the word extreme. I think atypical is a little more all-encompassing, and here's why, Danny. Extreme values, which mean the highest and the lowest. And I think that's it. Just because a data point is the biggest doesn't mean it's unusually big. And just because it's small doesn't mean it's unusually small. But if it's extremely big or extremely small, then we have to label it an outlier. But in order to know whether something's just the biggest or extremely big, what do we have to have? There has to be a gap that's well-defined. Thank you, Heidi. Yes, there has to be a well-defined gap that says, okay, if it gets past this, then it's unusual. So, and we call those in 244 critical values. It's the critical value. If you get past this value, anything to the right or left, depending on which direction you're looking, is too big or too small. The reason I like atypical is that also allows for us to include data points that are in between that are weird. Like if you look at data sets, for example, that have double humps, and then this little data point out here in the middle that's like floating around, that might be an outlier because it doesn't look like either of the humps that are in the data set. So that atypical kind of wraps all that up. But Heidi, thank you. Let's talk about the idea of critical values. Now I want to break this down into 3 areas. We might not get to all 3 today. I hope we don't actually. We'll drag this conversation into Monday too. But the idea of the 3, 1, there's many, many ways. There's many, many ways to kind of define outliers. And this has changed over time. Outliers. We'll talk about 3. We'll talk about 3. Hope you can read that terrible writing up there. Ways to define outliers. At least I spelled it right. Of course you can't tell because my penmanship is so terrible. Here's the first and very, very common way. This is, you guys have probably seen this if you guys have had Psych and Soc with Ken, for example. I guarantee you've seen this way without realizing that you're using this way. And there's a caveat to it. If 5 underlines, 6, 7, as many as you want. If your data is bell-shaped. And when I say bell-shaped, it will not be perfect. It never is. You never get perfect bell-shaped data. But if you can look at that data and go, arguably that's bell-shaped. There are ways to quantifiably measure it. You can quantifiably measure it by saying, let's check the skew. I know you guys love Pearson's. Let's plug it into Pearson, see what comes up with Pearson's. Nice job, by the way. Highest class percentage of those of you that found the skew command in Excel ever. Skew command in Excel, in the extra credit. I said I'll give you an extra credit point if you can find the skew of the data. Excel has a command for it. Highest percentage ever. I think it was almost 20% of the class found it. Well played. I think somebody in here got the factorial extra credit too. The 2013 with all the zeros with the exclamation point. That was a bastard move on my part, but we'll learn about that in your project number 3. It's okay, don't worry about that. Anyway, if your data is bell-shaped and you can calculate the skew, you can do all kinds of measures, normal quantile plots. All I want you to do in 243 is generate a histogram and look at it and go, you know what? That's about a bell shape. It might be a little skewed, but it's not so terribly skewed. We can make a critical value for skewness as well, Heidi. Like if it gets too far skewed that it's not a bell anymore, don't worry about that. Nobody can seem to agree on that anyway. So we'll just say it's roughly bell-shaped. If data is bell-shaped-ish, here's the rule for outliers. Any data outside of 2 standard deviations are considered, or are, I guess, depending on if there's more than one of them, are considered outliers. Very commonly used. Very commonly used. What it defines is, it defines the middle 95% of the data. And it says anything bigger or smaller than that, so the 2.5% above and or the 2.5% below is too big or too small. This has changed over the decades, but we seem to have settled in research on this measure of 2 standard deviations. You guys that have taken psych and social classes, the idea of a p-value ever come up in those classes? A p-value, do you know what percentage you're always looking for a p-value for statistical significance in research studies? Do you remember? It's okay if you don't. You're looking for 5%. And the reason you're looking for 5% is, what percent is within 2 standard deviations? 95%. So if something happens only 5% of the time, it must be outside of those 95. Go, Andrea.
What you're referring to when it's like p is greater than
Yes,
0.05.
ma'am. Yes, I am. Yes, I am.
Less than
Exactly. And when you see p is bigger than 0.05, the researcher puts his hands up and goes, you know what? Nothing unusual happened. Because it's within 2 standard deviations. But when it comes back less than 5%, like we're trying to see if green tea actually does decrease breast cancer rates. Holy crap, we ran some tests. The p-value came back at 1 in 1,000, 0.001. That's less than 0.5. That would be an outlier here. Which means if it's an outlier and we were checking breast cancer rates, we must have either a much higher or much lower breast cancer rate, hopefully lower in the case of green tea, which is what always seems to happen on those studies. John?
Is it 2.5% off each side?
It is if it's symmetric. That's a great question, thank you, sir.
Okay.
It's either depending on what kind of test you're running. The way I want you guys to think of it is 2.5 on each side.
Okay.
In 244, we get into one-sided intervals, and that's one of the, I'd save that for 244 because it's kind of a mind shift. You have to kind of deal with asymmetry. Think of it symmetric. Average plus for you guys. Average plus 1 down 1 plus 2 down 2, and you create the bell curve, right? If the data is shaped like this, there's your average. There's your average, yes? If you go out 1s and down 1s, this is x bar plus s. This is x bar minus s. What percent of the data is in there? Pretend those are symmetric. Careful. That's your 2/3, right? That's your 2/3. But if you go out 2 s's, s more, so it's x bar plus 2s, and x bar minus 2s, what's in here now? There's your 95, and anything in these tails will be unusual. So what John's question is, does that mean there's 2.5 here and 2.5 over here? Yes, because it's split symmetrically because of the bell curve. Thank you. Very good point to make. Very good point to make. So here's the question. Based on that definition of outlier, does the data set we were just playing with in that homework problem have outliers? I don't know. Let's look. It did have them, but that wasn't based on this definition. When your TI does outliers, it bases it on definition number 2, not this one. So we'll come back to that one, okay? And they don't always agree. Welcome to metric and imperial of statistics. Depending on who makes up the definition and which one becomes accepted, they don't always agree with each other. So it did have an outlier based on definition number 2, which I haven't even talked about yet. Let's look at that data again and see if we should even consider dealing with it in this way. I want to throw the screen, I think there. Can I erase that definition of outliers? I think you guys got it now. Keep asking those questions like John asked today, because this is probably the least, I know this class is pretty unmathy, I get that. But this is probably the least mathy of all the classes you've had so far, honestly. Because all of this is based on the definitions that have been handed down to us from those that create these definitions. All right, let's get this focused. All right. There they are. Okay, so first thing, I'm going to turn that box plot off. We don't need him just now. Just want to look at the histogram. So I'm just going into plot 2, turning that box plot off.
Do you want that over there? This?
Do I want?
No.
Oh, thank you, Christine. Yes, thank you, thank you. That damn GPS chip would fix all this. Zoom it in too. Perfect. All right. So now I can just go graph, and there's my histogram. Okay, definitely skewed. It's definitely skewed, right? I mean, it's leaning a little bit out to the side there. But would you call that a bell curve? If you had to give it a name, would you call it bellish? Yeah. I'm hearing some yeses. I'm hearing some yeses. If you say no, don't worry. We have a tool for that too. But I think that's arguably bell-shaped. If you want, real quick, I'll do this. I know you don't like to, so I'll do it for you. I'm going to do real quick, calculate skew for you, real quick for you. We're going to do a second, parentheses, X bar minus median, not picture, bar statistics, points. If this seems like magic, I apologize. It was the key shortcuts I showed you in that quiz from last week. And it's also it's in one of the one or two of the videos online too. So just try to real quick get a skew value. Boom! Skew's at 0.42. Hildebrand would go, it's too skewed. It's above 0.2. It's at 0.4. Too skewed by Hildebrand's definition. But who the hell is Hildebrand? It was the 80s. People were confused back then. So my point is don't get stuck by a definition of skew. Look at the curve and say, do you think it's bell curved enough? It appears to be. If you call it a bell curve, just act accordingly. I'm a happy guy. Okay. Now, once we have the idea that it's bell curve, we then have to create 2 standard deviations on that bell curve. So we have to find the average and we have to find 2 standard deviations. Now, I'm going to move this and not move it again because I want to write on the board. All right. This here, technically this is 0, this is 1, this is 2, this is 3, this is 4, and this is 5. But to keep it a little more easy for us to see, I'm going to put those in the middle. 0, 1, 2, 3, and 4. Because that does a better job of our discrete data. Because that's what actually happened. That's what we're representing. Everybody see what I just said there? When I changed my window, I made the high number 5 because the bar needs a width. So I'm going to put the numbers there just to make it a little easier to see. I ran 1 bar stats before. You might not have noticed. It did it kind of quickly. I ran 1 bar stats. I'll run it again. L1 and L2. So this is just like the baby weights from your in-class exams, just like everything we do when we have, oh, thank you, Christina. Just like everything we do when we have a distribution, you gotta run L1 and L2 with it. I get an average, so this is for the movie data. The movie data, we have voted that it is bell-shaped. X bar is that's about 1.5, yeah? On average, 1.5 movies. With a standard deviation of about 1.12. We'll call that 1.1, why not? We can also do this with the variable shortcuts. And again, this is one of those things I showed you on the quiz from last week with the X bar plus or minus 2s. I'll show you that again if you want to see it again. So here's what I vote we do right now. Let's take those statistics and create 2 standard deviations with them. Just like we did here, but let's do it on that curve. Danny, go ahead.
Oh, nothing.
Oh, just stretching, I'm sorry.
Yeah.
We just stretch. So let's do them on that curve, okay? Does that make sense? So 1.5 on average is going to be this guy right here. There's X bar. 1.5. I'm going to put X bar down here actually. X bar. And then we have to go out 1.1 twice or go out 2.2. Fair enough? So we're going to go 1 unit away from that guy, which puts us out here at 2.5. And then 1 unit again out here to roughly about 3.5. But if it's 2.2, what's that, 3.7? 3.7, let me put that in a different color so it stands out. 3.7, I'm doing some ishing here. This right here would go all the way out to X bar plus 2 S's. See what I did right there, friends? That number plus 2 of those. That's all I did. That number plus 2 of those. That's when we talk about 2 standard deviations, that's the top half of 2 standard deviations. Do the same thing for the bottom. Subtract 2.2 from 1.5. Now it goes negative. That's okay. That's okay. We deal with that. When you come down here, yeah, negative 0.7, right? Mm-hmm. That's going to be down here at negative 0.7. That's okay. You might say, none of our data is negative. I say, yes, that's correct. Which means what? There are no outliers on this end. Because in order for there to be an outlier on this end, we'd have to have some negative 1s, negative 2s, negative 3s, but you can't view negative movies. Unless you're me. Which you can. So yeah, there are no low outliers. The question is, are there any high outliers? by definition, yes, there is one. The 4, isn't it? Because this, Heidi, here's your critical value, friend. Here's your critical values. Your critical, let's mark them red, because that should be red, shouldn't it? Yeah. These would be called critical values. Those are the critical values. They are the endpoints of a, we'll call them in 244 a 95% confidence interval. A 95% confidence interval. Anything outside of that would be unusual, too big or too small. What are you thinking of right now?
Oh, no, I'm just, I agree.
You're with me?
Yeah.
Okay, cool, okay. It's just you had that look like, I've seen this before, I want to say something because I've seen it in a paper.
No.
Just taking it all in.
Yeah.
You're the man, you're the man. I'm sorry, and I do that sometimes, like I did it with Danny about 2 minutes ago. I see motion and I jump. I apologize. John, go!
Can't you just take your total number of data entries and multiply by 0.95, and if you come up one shy on either, you'll know you got an outlier on either
What are you
side?
assuming? What are you assuming?
And it's Gaussian.
You're assuming that you well, that's one thing. I wasn't even going that far back.
You know you have all the data, the
What-
total number of data points.
You're assuming you have outliers. So in other words, you're trying to force the largest data point to be an outlier, but it might not be. You see what I'm getting at, John? Like if we had changed that 4 to a 3,
But I know that like with this data set, I can take 24 and divide by 25, and it's roughly
95%, so there's gonna be one.
Something on the outside.
but there doesn't have to be one on the outside. And this goes more for smaller data sets than larger ones. With larger, normally distributed data, you almost inevitably have outliers, just by the function of there's enough of them showing up. Did anybody watch the video, the 68, 95, 99, 7 Excel video I made? I apologize for that one. I hit the F9 button and let just that happen, John. I let normal distributed data create itself for 4 minutes. So while you're watching the video, you actually watch a bell curve being born. And you'll do this kind of thing in your third project using Excel. I know, it's beautiful. And it needed a soundtrack, so I put a loud punk rock song behind it. And it was very loud, so if you might turn it down when you watch it. But the idea is, as you're holding down that F9 button, every once in a while he says, boop, boop. The guys on the end pop out, very infrequently, but roughly 1 in 20 times, which is what 5% is, it's 1 in 20. So you're right, just be careful not to force something to have an outlier if it doesn't necessarily have one. That's all I'm saying. I'm saying you're telling me how many it should have percentage-wise, assuming it has them at all. So don't force them to have them. That's how many would be an expected value, if you will. I love that idea. But just you realize it might not have any. And then, you know what, mathematically, suppose your data set's 10, right? And you multiply by 0.95. Well, you're going to get 9.5, which would mean that you have 9.5 normal points in here. And then you've got a half a point outside. And the fact that it's a half a point might make you go, maybe there isn't one, if it's only a half. So I see what you're saying, and there's validity to it. But just don't try to force outliers where there might or might not be any. Cool? Great point, though. Great point. Thank you.
I have a question.
Please answer that question, Heidi.
Okay, so can you go back to what you were saying about between the two red lines? It's the 90.
It's called a confidence interval in 244.
Okay.
This range of values, you would make a claim that I'm 95% confident that whatever I'm looking for lives between negative 0.7 and positive 3.7.
So you said 95%, not 90.
95, yes.
Okay, good.
Oh, 95, yes.
90, and I'm like, but it's 95.
It's 95. It's not by the fact that it's 2 standard deviations.
Right.
If I went 1 standard deviation, I would only be 2/3 confident.
Right, okay.
Yeah,
That's
you
what
could
I'm
adjust it to
saying.
90 if you needed. I think with 90 it would be like 1.6 or something like that. You have to go out like this far.
Okay.
Cool? Fair enough? So that's how you would identify 4 as an outlier in this data set using that tool right there. So there's one way to do it. There's one way to do it. Fair enough? Fair enough. Now, that's not always the case. Let's identify, that's not what the TI used when we graphed the box plot. When we graphed that, I'm going to turn that box plot back on now. Second stat plots, plot 2 on. And I'm going to leave that funky box. You know what? No, turn the other box plot on. Turn the one without the mark on. We'll turn the 4th option back on. Turn that 5th option on right now, the one without the mark. And then just hit graph, and the box plot will sit up top there. This is kind of unfortunate. I'm going to pull this screen down momentarily. Now I know, I could tell by looking at that number on the outside was going to be an outlier. Only because I knew what definition of outlier the TI is using right now. The TI is not using standard deviations to measure outliers at this point. It's using just the box plot itself. So what the TI is doing is, it's taking its hands, it's measuring how far apart this box is, it's taking that distance, increasing it by 50%, and then stacking it. Remember me doing this on Monday? I did it on Monday with your guys' data. I think I nailed everybody. You guys have outliers, you guys don't, you guys do, you guys do, you guys don't. It takes this box width, increases it by 50%, drop, drop. Anything outside of that would be considered unusual by that definition. Now notice how that's not the same as what we just did. And that's why this has actually got a different name. Number one would be if your data is bell-shaped, use 2 standard deviations. That's one. This will still work if it's bell-shaped, but this way also works when it's not. And I'm going to try to generate some goofy data for us in a couple of minutes. I'm going to ask you guys to collect some data sets for me. We're going to see if we get any goofy asymmetric data. I think we can. I think I can force it. So method 2, I call this the IQR approach. And all IQR stands for is interquartile range. Yeah. Interquartile range. That's what the IQR stands for. An interquartile range is just the distance between the quartiles, Q1 and Q3. It's how far apart they are. So the IQR is defined to be Q3 minus Q1. In our case, that's pretty boring, isn't it? Because I think Q3 is 3, and Q1 is 1, right? So Q3 was 2, I think. Wasn't it? Check it for me.
Yeah.
I think P90 was 3. 90% was 3. Yeah. I think, check me on this, I think Q3 was 2. Yeah. Okay, so Q3 was 2, Q1 is 1, so the interquartile range, and John, only question because I looked up at the box plot right before you said that, and I saw they're 1 apart. Now, if you don't have to remember this, you just go back to one of our stats and look. It's sitting right there for you. And remember, the weirdness was the median was also 1. Remember that? That's why there's no median line, because it's sitting on top of Q1 over there. So what the IQR method does is it takes the IQR. Now here's the part that's kind of human-made. It takes that, multiplies it by 1.5, which is the same as adding 50% to it. Fair? Okay? So in our case, that would be 1.5 exactly, because it was 1, now it's 1.5. And then it stacks that number outside of the quartiles to set up critical values. So you use that, use this to set up the usual or typical range. And you know, honestly, I've tried to do this algebraically for years, and I'm not going to do it. We'll do it on the actual graph. I think you guys will actually see that on the actual graph much more easily than trying to do it with the algebra. Q3 plus 1.5 IQR, Q1 minus 1.5 IQR. I'm sure it's in your textbook. But let's just see it on the actual graph. On the actual graph. Now I'm going to have to mess with this a little bit to get it to fit. I'm going to slide this down a smidge. There we go. I apologize for messing the graph up there, YouTube world. There we go. All right. Now please realize the way I've labeled these numbers, the box plot's actually in the wrong place now, isn't it? The box plot is shifted over a half a unit from where it should be. If you think about it, because now it's gone. So if you think about it, I've got this dotted line at 1.5. That's Q3. It should be at 2. So I did that to make it easier to see the histogram at the bottom, because this is actually 0. That's actually 1. I shifted everything to make it easier, more logical to see in your mind. So you have to imagine the box plot over a little bit. It's not going to matter. We'll do it numerically. So this is supposed to be 2 right here. And this is supposed to be 1 right here. Now follow with me here. We're going to set up Heidi's critical values. Here we go. There's our marker length, the 1.5. Take that 1.5, add it to the 2, and see what you get. you get 3.5. Anything outside of that is too big. Anything outside of that's too big. Guess what? We have a 4. That's why that's an outlier. And that's why 3 is not an outlier, because 3 is inside of that. Same thing on the bottom half. Same thing on the bottom half. You take the 1, subtract 1.5, you end up at negative 0.5. Nothing's negative, so nothing's unusually small. But the fact that we have something outside of the top means we have a high outlier. Do you see how they're not exactly the same ranges as the bell curve ranges? They're off by 2/10 of a unit or something like that. That inevitably happens. And the more skewed the data, the worse that gets. And when I say worse, I don't mean worse in a bad way. I'm just meaning the more deviant they get from each other. And that's why sometimes, if you choose one way to generate outliers, you'll get one result. And if you choose another way, you'll get a different result. So it all depends on what the way you choose to do it. One way, this only works with bell curves. That works with pretty much any set of data at all. So a lot of students just say, the hell with it, let's just use that one, because it always works. That's the one your TI uses. That's why when you change plot 2 to a modified box plot, which is what this bad boy is called, modified box plot, that's why it shows the outlier up there. It's due, because look tight, it is doing that outlier. It's doing that outlier based on the interquartile range, not the standard deviation. Sorry, Dan. I had to watch that. It's doing that based on the IQR. Now, they don't always agree. Sometimes the data set will generate outliers one way and not generate outliers a different way. So it's just a matter of whatever way you choose to do it. This is a fairly common way using the IQR. So what I want to do right now, John, go, please.
I just have
Please,
a question.
go.
So what happened to our 2.5%?
Oh, that doesn't exist outside. We weren't looking at the 2.5%, 95% in the box plot.
Second definition, that goes away.
It never was ever there.
Okay.
It's a totally independent way of finding outliers. It just so happened they were fairly close.
Right.
But what this does, and there's no fixed percentages attached to it. John asked a very good question right now, if you caught it. What happened to our 95, 2.5%? There's no fixed percentage anymore. What they essentially do, see if you can work through me here, they find the IQR. That's what percent of the data it lives between those two distances. Half of it, 50%. Then they increase that by 50%. So technically, it's kind of like 75%. And then they stack 75% on top of Q3, which would essentially go out 75% from 75%, which kind of puts it out at 150. But now we're really stretching the idea of a percentage here, right? Because that would mean nothing could be an outlier, because you can't be over 100%. So the idea of percent kind of gets washed out the window with the IQR way, and it's strictly a measure of distance, not percentage within a distance. It's more general in that respect. It's less stringent. That's a fantastic question. Thank you for that. So yeah, there's nothing to worry about there other than pure distance. And did you get far enough away? Also, timeout. That 1.5 times IQR I mentioned back here, did anybody question, why did we multiply by 0.5? Yeah, good. Dale was like, yeah, you just threw that out there like it was okay. It isn't necessarily okay. If you do 1.5, it's what most textbooks will term mild outliers. If you multiply it by 3, which is twice as extreme as 1.5, anything outside of those are called extreme outliers. Who says, is this that bastard Hildebrand again? I have no idea. Somehow those ranges have been agreed upon. So again, statistics has made up a lot of this. It's a lot of these things that have been kind of rolled along with us. This one is way more probabilistic, which is, I think, is why it's more popular in research methods. It tends to show up with more precision, if you will. That this is kind of more seat of the pansy.
Because you can use a percentage.
You can actually assign a percentage to it, where you can't really do it here. It's a strict distance. Thank you for that awesome question.
So my next question is,
Go, yeah.
if you don't mind.
No, dude, not at all.
So you want us to stick with that 1.5 always, or do you want to go to that 3?
Use the TI.
Okay.
The TI is doing 1.5 for you.
Okay.
If you've got to do this method, use the TI to do it, please. Just turn the modified box plot on and graph it. And if the outlier's there, that'll show them to you. Is that fair? Now the one thing the TI will not do, just careful, the one thing the TI will not do is show you if you have more than one of the same value. So if you had 2 4s, let me see if I think I can force this to be deviant. Let's see if that changed one bar statistics enough. Nope. there are now 2 outliers, 2 4s. What I wish the TI would do would stack those 2 at the end so you know there were 2 of them. You see what I'm getting at? So, and if you hit trace and you're up there, if you hit trace on the modified box plot, it'll show you the min, Q1, median, Q3. Notice how it calls that X? It doesn't know what to call that. We can make up a name for it. It's the largest, least atypical data point. But that doesn't fit very well on a small screen, so it's just X. And then, boom, there's the max. Can I press it again? No, it's just registering it once. That's a downside. So if you have lots of outliers in a very large data set, your TI is going to do kind of a crappy job showing you how many. So that's why you want to go back to your distribution and look, or your histogram. You may have noticed the histogram bar just got twice as big over there. So that's why you kind of have to look at that as well. So I'm trying to say this is one more tool for the toolbox, not necessarily the only tool. John, is that fair? So yeah, please use the TI. Stacey, yeah.
I got lost somewhere there. I just watched you add the 1.5 to the 2.
Oh yeah, I took the 1.5. That guy over there.
Yeah,
and then I just stacked that distance on this and on this.
Okay, I guess what I'm asking is what happened to the multiplication you told us about? I got lost on that.
Of the 1.5?
Yeah.
But well, 1.5 times 1 is 1.5. Our IQR was just 1. I just kind of wrote it as 1.5. I think you didn't have to see 1.5 times 1.
I'm totally lost that.
No, you're not. No, you're not. No, anything times 1 is itself. You
I
have
know that.
Well, yeah, you do. That's why I know you're not lost. Please, Heidi.
I'm just trying to logically get this in my head.
Good.
The 1.5. So does the 1.5 determine how far an outlier needs to be in order to be an outlier?
Yes.
Basically.
That's exactly what it's doing. But instead of measuring it from a center point like the average, it's measuring it from 2 asymmetric points, Q1 and Q3.
So to go back to what he was saying about is it always 1.5? I mean, if you're trying, I don't know, I'm trying to get this in my head enough where I can make this logical question.
Deviations, it's just the number that we use to put on each side to determine. It's
But you
basically the
can
same
change-
concept.
Of course you could.
Change that number
Of course
because
you
you
could.
figure out
And people can do that. If they've got 2 deviant data, they'll make it bigger to cut on the number of deviant data points.
So it's not as.
We call this crap statistics. Right? If you've got wildly deviant data but you want to make it look less deviant, change it to 3.
Right.
That pumps out further where deviant has to be and probably knocks down the percentage of those that are deviant.
So it's not as static.
It doesn't have to be.
Yeah.
That generally used is 1.5. Generally used is the 1.5. Yeah.
Are we going to do this with another data set?
We're going to make one up here.
Bigger one?
I want to make sure you guys questions get answered first.
Because I
Though.
don't get it.
Well, yeah, you do. You do. You get more than you think you do. Okay, here we go. We have a request for a data set. Here we go. I think we have time for 2 more.